So I wanted to do a classic example of an application of using Gauss's law to find the electric field. Now I know they do this in the book, but I was hoping that if I walked you through it, you would find that helpful. So we're going to imagine a scenario where I have a solid sphere of radius big R. If you want to think of a number, it's okay. And the total charge on that sphere is big Q. But the thing is that this is like a solid ball, and the charge is all spread out within the sphere as well as on the surface, so it's all throughout. It has a uniform charge distribution, which means that we can talk about the charge per unit volume. You see that familiar letter rho, which is typically used to talk about things per volume. And in this case, it means the total the amount of charge per volume. And so if we think about the total volume of the sphere, this is where some of your geometry facts are going to come in handy. This volume of a sphere is 4/3 pi r cubed. And so if we take the total volume of the sphere, we get the total charge. What we're going to look at in the second part is if we take a smaller part of the sphere, like if we took the inside part of it, we're going to get a little bit less than the total. But in this first example, we're going to look outside of the sphere. And that's why this little r, this is where we're interested in, is bigger than the radius of the sphere. Now, before we get into applying Gauss's law, I want to talk a little bit about some basic things that we need to know and we keep in mind to use it in a helpful way. So it turns out Gauss's law is, we're trying to sell it to you as a much easier way to find an expression for the electric field. In the previous chapter, we saw some examples where you could calculate the electric field due to a charge distribution. It involved a lot of integration, figuring out angles, thinking about what components cancel out, and I'm just going to make a wild guess that you didn't find any of that very much fun. This, using Gauss's law, is going to be a lot easier. It doesn't work every time. It works in certain scenarios. Now, you're going to say, well, hey, there's an integral, so what are you talking about? I still need to integrate. To be honest, the amount of integration you have to do is trivial. It's like integrating dA. What do I get? Oh, A. So it's not like a real hard integral to do. Now, let's talk about this expression. This is what we're going to talk about in class a lot. It's called electric flux. It's the amount of electric field that goes through a particular area. The way we can calculate it is we construct a closed surface that has an area, and it's going to enclose our charge distribution that we're focused on. And so that's what this little circle on the integral means, that because our integral is over the area, it's a closed area. Now we're looking at how the electric field and the area dot with each other. Remember, that's the dot product or the scalar product. What we're trying to do to make this a simpler integral is we're trying to find an area where the area itself, remember that's vector direction is indicated by a vector that's perpendicular to the actual surface. So we want that vector area to be parallel to the electric field, or in some cases perpendicular. If it's perpendicular, this dot product gives 0. If it's parallel, then you just change it from a dot product to just simply E times dA, and you don't have to do the vector notation. Finally, what we're trying to also find is an area so that that electric field is constant on the area. Okay, so we're thinking about a couple of things. We want some sort of area that the area vector and the electric field vector are parallel to each other, and we also would like to find an area that the electric field is constant on. Now, the reason that we start with a spherical distribution is a spherical distribution of charge, like a big ball of charge, is very similar to a point charge. So we have some expectations that the electric field that is created by this charge is going to radiate out from the charge itself. And keep in mind, so does the area vector. And so right away, I can kind of get a sense, what would be a really good surface? Here's another piece of information that's really helpful. We usually will choose a surface that mimics the geometry of our charge distribution. So I'm going to choose a spherical surface. So that becomes the surface that I chose. It has a radius, a little r, that's bigger than the radius of the charge, the sphere of charge. And so now we're going to use that. This is our surface. And now we're going to work with the Gauss's law. And we're going to gradually be able to simplify this piece of it using some of the facts that we see. So the bigger arrows, I said, represented the electric field. I labeled one area. The area, of course, would go all the way around the sphere as well. So in general, the electric field and the dA are parallel to each other. So their dot product can be rewritten as just the product. No vectors, no dots, pretty easy. The other thing is that because the electric field lines come out radially, I could assume that at a constant distance from the center, the electric field is going to have the same magnitude. And so it's going to be a constant. And so that means it can come outside of the integral. Now I just have the integral of dA. And if I integrate that, just get area. What's the area? It's the surface area of a sphere. If you don't remember what it is, you're going to soon be in a position to remember it. It's 4 pi r squared. Now, what we've done is we've sort of dealt with this part of Gauss's law. This is equal to the charge enclosed over epsilon naught. Well, think about it. For that green dotted surface, how much of the charge have I enclosed? All of it. So I just put big Q in there. And I'm going to solve for E. And I get, this is where you see that 1 over 4 pi epsilon naught. I think that that's part of the reason our book chooses to introduce electric field with this constant, because you'll see it in Gauss's law and then it'll become more familiar to you. I still prefer to replace it by the K because it's less to write. I mean, come on, looks simpler. But what I want you to notice about this expression is, what does this look like? It looks like the electric field of a point charge. It's almost like this whole big sphere created an electric field equal to the electric field of a point charge if the point charge was right at the center of our sphere. That's something to remember. So this was part 1 of using Gauss's law to figure out the electric field of this charge distribution. In the next video, we're going to look at what happens if we want to look inside of the charge. What does that electric field look like?